So it's going to be important for us to understand the distinction between a population and a sample. That's going to be vitally important to us. It's not going to be that important because you're never going to work with a population in real life. You're only going to work with samples from a population. But it's still important for you to understand the difference between the two. So I'm going to give you a few examples and ask you to think about whether these things are populations or samples. Okay, how about everybody in the United States? Population. Good, that's good. Okay, how about everyone that lives in Brooklyn? Everyone that lives in Brooklyn, everybody. Population. Everybody that's in this building right now. Population, right? Because it's everybody, right? Everybody that's in this room. Population, right? It's a small population, but it's a population. Now, what if I asked you, I want to find out the average weight for everybody in Brooklyn, right? Or the average age, let's say. We're going to find that out in about a year or so, right? Because what's coming up next year? The census. They're going to run and survey every single person, or everyone that they can nail down and catch. They're going to, actually, I think legally required to fill out that census paper, right? They can go chase, I don't know, I've never heard anybody go into jail, but I'm sure they can make it unpleasant for you. So at any rate, so the census is coming up. So if I were to ask a question like, what's the average age of everyone in Brooklyn? That would be a question you might be able to answer. What's the average family size for all of Brooklyn? That's something that when the census comes up, you're going to be able to answer. However, until the census, on a practical basis, we're not going to be able to do that. If I needed to know that now, and I didn't have the resources to go and survey everybody in Brooklyn, I would take a sample from that population instead. So I might say, I'm going to sample 1,000 people in Brooklyn. Okay, so I'm going to randomly select 1,000 people in Brooklyn. How am I going to do that? Maybe I'll do that with phone calls. Maybe I'll do that with students that like interns. I can send them out into Brooklyn and randomly pick blocks and so on and so forth. So I need a mechanism where I can make a random selection, a true random selection, because I don't want to just go to one neighborhood in Brooklyn if I want to understand what the average for all of Brooklyn is, and I don't have the resources to measure everybody. So if I want to know what the average age of people in Brooklyn is, I'd randomly select, say, 1,000 people. Could be 100 people, could be 2,000 people. In any case, it's not all of the people, it's a sample from that population. Now, what would I expect the difference between the mean of the population if I sampled everybody in Brooklyn versus the mean of the sample of a large sample like 2,000 people that I took in Brooklyn randomly? What would I expect about those two means? They'd be, we would hope they'd be pretty close, right? I mean, that's why we take a sample. That's why we're concerned about the size of the sample, because we want a reliable estimate of what the true population mean is, right? So the mean of a sample approximates the mean of the population, okay? What about the spread? Like, in other words, remember that we talk about variance, standard deviation, in other words, or even just minimum and maximum, the spread. How would we expect the spread of ages in the population to compare to the spread of ages in the sample? About the same, right? We would expect the same kind of spread. We get some old people, we get some young people, we get more people in the middle there, probably somewhere, right? So the spread and the mean of the sample approximates the spread and the mean of the population. So it makes it a good tool for us. When we don't have the resources to sample everyone, we can use a sample to approximate what the population looks like. Give us information about the population. Bigger the sample, the more information it gives us about, the better the information is that it gives us about the population, more reliable the information is, okay? And we're gonna be taking a look at that. We're gonna look at the dynamics of sampling. Why is that so important to us? Because since we're so dependent on, because from now on, except for the census, the only picture we're ever gonna get of a population is what we get from a sample from that population. Okay, so it's vitally important we understand the mechanics of this, how this sampling works, how it's going to, what we can rely on, what we can't rely on, how much certainty we have about the results we get from a sample. Okay, so let's think about this for a second. How are we going to take a look at that? So what I'm going to do is I'm going to take a population, and there's a document on Blackboard called Introduction to Sample Distribution and Central Limit Theorem, CLT is Central Limit Theorem. And there is a grid there. It goes from 0 to 9 columns, 0 to 9 rows, so there's 100 numbers in there. You know, those numbers are just numbers. They're approximately normally distributed. That's the way those numbers were created. But, uh-oh, my goodness, we seem to have a little problem there. And of course, nobody told me about it. Hang on a second. There we go, that's better. Now you know what I'm talking about. Actually, it wasn't so bad, right? Because I wasn't really using the screen up to that point. Okay, so let's take a look at these 100 numbers here. Okay, take my word for it, they're approximately normally distributed. Let's, you know, they don't really represent anything but numbers. I'm going to make something up. I'm going to say that those numbers represent insulin sensitivity, a number, a measurement, a blood test for insulin sensitivity, right? And I randomly select, oh, excuse me, this is the entire population that I'm working with. It's 100 people, a population of 100 people. Could have been 10,000 people, could have been 1 million people, could have been 10 million people. This is the entire population. So if I want to know what the average insulin sensitivity for this population is, I could go over here. Well, I could use Excel, right? So as a matter of fact, on Blackboard, you can open an Excel file that you can download, which is this same table in Excel. Okay, can you guys see that pretty well? Let me zoom in a little bit. Okay, maybe a little bit too much. I'll zoom out a little bit. Okay, well, I can see almost all of the table there. Okay, so if I want to know what the average insulin sensitivity in this population is, I can just say that it's equal to the average of all of these numbers, all of these 100 people that make up this population. So the average insulin sensitivity in this population is 50. How about the variability? What number do I usually use for variability when I'm looking at a population or a sample? Equals standard deviation. Well, what's the standard deviation for this population? I'm going to do the same thing here. The standard deviation, which represents the variability, is approximately 9. Now these are round. I think this is purposely rounded off the whole numbers. What do I use? What letter do I use to describe the mean of a population? Anybody remember? U, right? Okay. When we're working a population, we always use Greek letters. What do I use to describe a standard deviation? I can't draw it, so I'm just going to type in sigma. Right? Sigma, that little circle kind of thing. Right? So the mean of this population is 50. The standard deviation, a measure of the spread, is 9. So what do I know about this population already? Well, I know that 95% of the insulin sensitivities in this population is between 18 less than 50 and 18 more than 50. Right? Because if I told you ahead of time that it was normally distributed, 2 standard deviations below to 2 standard deviations above. So I kind of got a feel for it. That standard deviation gives me some information about spread here that I can understand. It'll help me out, right? So let's go a little bit further now. Now let's say that I have another population, okay? Except it's really the same population, but I'm going to make believe it's another population. Let's say I don't have the resources to measure the insulin sensitivity for everybody in this population, okay? So instead, I'm going to randomly select 9 people from this population, making believe that I don't really know what the mean and the standard deviation is. I'm going to randomly select 9 people from this population. I'm going to calculate the average and the standard deviation for those 9 people, those 9 randomly selected people. So I'm going to do that. I want you guys to do that too. Randomly select 9 people from here and type it into, you can either type it into the chat box or just yell it out at me. Okay, and you literally, for now I'm going to go back and talk about this randomness in a second. But for now, I'm going to be satisfied with doing this way. In other words, pick a 1, 2, 3, just kind of pick out 9 people randomly. Put those numbers on the side here, like, I don't know, 49, and pick, blindly pick another one, 40, 50, 47, 43, so on and so forth. Pick out 9 numbers, find the average and standard deviation for me. Is this really a random sample? Is this a truly random sample? Well, no. It could be that if your dominant eye is your right eye, you may pick out more people on the right side. If you're right-handed, you might pick them out. You might have a tendency to pick out high numbers, not low numbers. Not really random. I'm going to let you guys get away with it for now. So I want you to pick out these numbers. Right? I'm going to pick out 9 of them. What do I got now? 6. Okay, I picked out 9, I think. 1, 3, 6, 9. Oh, I got more than 9. I don't need that one. That's 9. Okay, so I'm going to add them up, divide by 9. That's going to give me my average. Equals average. Parentheses. The average of these 9, the sample of 9 is 46, under what the mean was, right? And the standard deviation is 9. Wow, got pretty close to the standard deviation. I got lucky. I got very close to the standard deviation. Mean I was a little off on. So what did that tell me about that sample? That sample approximated the mean of the population. Wasn't exactly the same, a little bit lower, but it was pretty close. It also approximated that the sample distribution, the sample I have here, also approximated the way that the population was spread out. Okay, so I'm going to put 46 over here. That's my mean. Anybody else got a mean for me now of nine people? 53. Good. Okay, next. I'll look in the chat box, see if anybody's putting them into the chat box. Oh, good. I got a 46 there. Another 46. Anybody else? What have you been doing out there while I'm talking? 52. Okay. I got all night. I'll wait here. We're going to get through this. I'm going to take a few more numbers, and then we'll get through this exercise. And then I want to go back and maybe try it again once more. But first, before we go back and do it again, I want to discuss this idea of randomness. Because this isn't really truly a random sample. I haven't given you a mechanism to really take a random sample here. Can a computer generate numbers randomly? Anybody? What's your opinion on that? How does a computer work? How would you tell a computer to generate random numbers? You have to program it to do that, right? So if you program it to make random numbers, is it really random? Kind of hard to tell, right? Maybe, I don't know. How do they generate true random numbers? Used to be, there's a lot of different ways to do that. If you type in random on Google, there's an organization, random.org. You can go there and give you all sorts of information, random numbers. They used to use radioactive decay, which was which is distributed in a certain way, and it's not very predictable. And they used to use radioactive materials, radioactive decay, and scintillation counters to generate random numbers. Nowadays, they use quantum mechanics. They use the behavior of photons and this thing with spooky bodies where you can have, like 2 bodies remotely from each other, and one you change one, it also changes the other, but they have no apparent connection. And like if you read about it, since you don't know what kind of effects it generates before it actually happens, you could say that it's random effect, a 0 or 1. You can't predict ahead of time what it's going to be. So that's supposedly true. This quantum effect is truly random. I've read it about 20 times. Every once in a while, I kind of like think to myself, I actually understand it, and then I blink and it's gone. So, but that's the way they would create real. I mean, creating something that's truly random is not that easy. But you can get pretty close to random, even with computers. Okay, any more numbers here? How much? I'm sorry. 29 was it? 49. Okay, good. I didn't think it was 29. Okay, next. 45. 48. 51. Okay, I'll take one more. 56. Okay, so now each one of these 9 numbers came from a sample, right? Just like I did here. Each one of these 9 numbers came from a sample. Let's say I did this 1,000 times. We had a classroom, 1,000 people. Everybody randomly took 9 numbers, found the mean, right? Well, what can you tell me about if I were to now make a new distribution from only the means of the samples that I took of size 9, right? My sample size here is 9, right? If I were to take the mean over the mean of a sample size 9 over and over and over again, what would that look like? Well, what's the average going to look like for all of those values? Anybody want to give me a guess before I do it? It's going to look very similar to the sample mean, right? What's the standard deviation going to look like? Somebody predict it before I actually type it. It's going to look like 9, you think? It's not 9. It's a lot smaller than 9. Why is it so much smaller than 9? Because the means are bound to be closer. The means of each individual sample are bound to be closer to the true population. They're not going to be spread out as much, right? So in the population, the smallest value in here looks like it's going to be like 32 or something like that, right? But are we ever going to get, if I take 9 people randomly, am I ever going to get a mean of 32 for them? No, because that's only the smallest, the lowest value. I'm never going to get it as spread out. So this sample distribution, or any sample distribution, is going to be narrower. It's going to have a smaller standard deviation than the population standard deviation. The mean of the sample distribution is going to approximate the population mean, but the standard deviation of the sample distribution is going to be smaller. Now, I'm not gonna beat this to death. I'm going to tell you up front that if you do it for an enormous number of samples, do it 1,000 times, 100,000 times, 1,000,000 times, take away chance and variability. If you do it many, many times, it's going to turn out to be that the standard deviation of the sample distribution is going to be the square root of the population standard deviation. So if I did it many more times than this, we would expect that the mean would be close to 50, but the standard deviation of these repeated samples would be probably like 3, the square root of that 9, about 3. And we got pretty close to that result, didn't we? We cheated a little bit. It wasn't really a random sample, and I did that because if I told you to make a truly random sample, we'd be here all night. It takes a long time. I never get enough numbers in a short enough period of time. But just to show you a couple of ways that you might do it, you can go to Google and type in random numbers, random number generator. And what comes up but a random number generator? And I can tell it that, for instance, let's say I want to tell it that the minimum value is 0, 0, and the maximum value is 99, and say generate a random number. Comes out to be 51. You could then go back to our table and say, well, my first number is going to be row 5, column 1. So I'm going to say 47. Now you can go back and do that again. Okay, now 6, 7. I'm going to take the row 6 and the column 7. So my next number is going to be a 50. and so on and so forth. You can do that to get your random sample. You can also go to a site called random.org, which has a number of different random, whoops, I don't know, radio link, random.org, right? And they have a number here. You have a lottery quick click, a random number generator for numbers from 0. What's the biggest number in the lottery these days? It's like 60 or something like that. It will generate random numbers for you. And you can tell it, like, you can give it some schemes if you want, and give it, range, and tell it to include some. But there's all sorts of different programs here that generate random numbers, different conditions. Another way that you can do this, there's actually published lists of random numbers. So let's see if I have it here. This is from a textbook. Actually, a book that this is from a statistics textbook. It's it's one of the appendixes. It's a random number table. So you have all these tables that are just random numbers that you can use for studies and things like this. Like, you can hold on to this if you have to do a random sample in the future. You can actually use this table. How would you use this? Well, I just randomly pick one table, one page, and I would start anywheres in here. I'm going to start right here. And you could say, well, since I need random numbers, row and column for 10 by 10, I'm going to take a 2-digit number. So my first 2-digit number is 15, row 1, column 5. My second 2-digit number is 46. And just keep going like that consecutively with these numbers. And that would be generally a fairly random selection of numbers. Okay, so you have a lot of sources for random numbers. So really, by all rights, we should have done something like that instead of letting you just pick numbers, all by yourself just by pointing at them. Right? So, but I wanted to speed things up a little bit. Okay, so let's see what we can do with this information. So now we understand a little bit more about the dynamics of sampling. And let's see if we can't do something useful with this. Let me go back to my table here. Okay. Okay, so this first problem is going to echo what we've been working with before, which is a population. Right. So we want to understand, when we take a sample, how does it impact our understanding of what how the population distribution looks? So for starters, let's go back and take another look at the population distribution. If total cholesterol values for a certain population are approximately normal, with a mean of 200 milligrams per 100 milliliter, and a standard deviation of 20, find the probability that an individual picked at random from this population will have a cholesterol value between 180 and 220. That's a pretty easy one, right? Because the mean is 200, the standard deviation is 20, and we're talking about the population now, right? So what do we know about the population? Between 180 and 220, what percentage of the population is between those two numbers? One standard deviation below and one standard deviation above is 68% of the population, or 68.1 or something like that, right? So that's okay. How about between 160 and 240? 200 means 200, where 40 below, the standard deviation is 20, where 40 below that and 40 above that, 2 standard deviations below, 2 standard deviations above. What percentage of the population is between those two? 95%, right? Empirical rule. So, okay, so I know that percentage of the population is between those two numbers if it's a normal distribution, right? So I also know if I pick one person at random, since 95% of the people are between those two numbers, the probability I'm going to pick one person that's between those two numbers is 95%, because that's the percentage of people between those two numbers. How about greater than 225? Oh, okay, now things are going to get a little bit sticky. So now we're going to have to take a closer look at this. And I'll use as an excuse to actually draw this distribution. Oh, there it is. Okay. All right, so I'm going to draw this distribution. So it's a population. I told you that it was normally distributed. So it's going to look like a bell curve. It's going to be symmetrical. The mean is going to be in the center. And mu, since it's a population, I'm going to use mu, is equal to 200. The standard deviation, I'm going to use sigma because it's population, is equal to 20. And I'm asking about the probability that you would randomly select someone that's above cholesterol value above 225. Know what it was? Let me just check it. 225. Yep. Okay. So the probability is equal to the proportion, the area of this part of the curve here, right? In other words, what percentage of the curve does this represent? What percentage of the people are above 225? That would be the same as the probability of picking one person that's in that area if I pick randomly. Okay, so how do I figure that out? Well, in order to figure that out, I have to calculate a z-score. I have to know how many standard deviations above the mean that it is. When it was 220, it was easy, right? Because it was exactly one standard deviation above the mean. But now it's 225. So I'm gonna call it a z-score, number of standard deviations, same thing. X minus mu over sigma. Okay, X is the value I'm interested in, which is 225, minus 200, the mean. Notice it's going to come out to be a positive number, positive z-score, because it's to the right of the mean, over the standard deviation, which is 20. So that's equal to 25 over 20, which is equal to 1.25, 1.25. Okay, z-score plus 1.25. So how do I figure out what that area is? Well, we can go to a z-table for starters. And the z-table will tell us, oops, back there. The z-table will tell us the area to the left of 225. Well, since this represents 100% of the population, if we know that area, we can just subtract it from 100% or from 1 to get the proportion of the distribution that's above 225. Let's do that. Z-table. Here we go. Okay, so it's a positive z-score. You notice the shaded area is to the right of the mean. So it's 1.2, okay, and the vertical columns represent the third digit. 1.20, 1, 2, 3, 4, 5. 1.25 is going to be this number right here, which is 0.8944. So this is 0.8944, or about 89.5, right? So what's going to be left here is going to be 1 minus that, or 1056, 0.1056, or about 10.5%. Okay, so it's probability of you picking a person that has randomly from this population, it's a cholesterol above 225. It's a little bit more than 10%, about 10.5%, or 0.1056. Okay, so what's the next part of this? Okay, how about a cholesterol level less than 150? What's the probability of selecting someone with a cholesterol level less than 150? Let's say it's 150. So this area would represent that probability, less than 150. I'm going to leave it up to you guys. You guys calculate what that is. I'll give you a minute or two to do it, a couple of minutes to do it. Okay, calculate the z-score. Z is equal to x minus mu over sigma. Keep in mind that now x is less than the mean, so it's going to be a negative number. Nope. If you get finished early, you can type it into the chat box, or if you're shy. Okay, so what do you guys think the z-score is? Negative, what is it? 2.5. Okay, 150 minus 200, right? I'm going to do sketch. 150 minus 200 is equal to minus 50 over 20, which is equal to minus 2.5. Okay, minus, keep in mind, minus is important, right? It means it's to the left of the mean. Okay, and what area does that represent? Get the Z-table up. So this I'm going to use the one table that represents the left side of the mean, minus 2.5. What area is that? 0.0062. Did I get that right? Oops. Get back to the table here. That area, I didn't draw it very well, did I? Equals 0.006, I think I said 4, right? Less than 1%. So that represents less than 1% of this population. Probability that you would pick someone with a cholesterol level under 150, total cholesterol level below 150. But this is not real life, right? So also this could go back to the days when I first started getting my cholesterol level checked. And you know, everybody's they say bad cholesterol is like 300. Now things have changed a little bit. So, and people used to have higher cholesterol back in those days. Okay, so that's how I would handle this. Let me see if there's one more there. How about between 190 and 210? I think it's worth doing this exercise. Between 190, here's 190, and 210. Okay. Well, how might we figure that out? Well, think about the areas here. 210, if I'm going to use the Z-table to figure out areas here between 190 and 210, if I calculate the Z-score for 210, 10 minus 200 over 20 is equal to plus 0.5, right? Okay, if I look up that Z-score and on the table, and I look for this area, I'm going to find the area from 210, or plus 0.5 Z-score, all the way covering the entire area below it. Then if I look at 190, well, 190 is going to be 190 minus 200 over 20. That's going to be equal to minus 0.5, right? And if I look up what that area represents, it's going to be everything from here down. So if I take this area and subtract this area from it, what's going to be left? It's going to be the area in between the two of these. So I can use that to figure out what's the probability of choosing someone that's a cholesterol between 190 and 225. Everybody comfortable with that? Let's actually do it. Let's not so much. Let me draw it again. I saw a couple of waving hands here. Okay, let me sketch this again. Okay, so the mean is 220. That's mu. Sigma is equal to, remember, working with population here. Sigma is equal to 20. I want to know what's the probability that we would randomly select people whose cholesterols were between 190 and 220. Okay, well, I just calculated the Z-score for 220, and it turned out it was 210, I think, right? 210. The Z-score for 210 came out to be plus 0.5, 1/2. 210 minus 200, 10 over 20 is 0.5. And the Z-score for 190 was minus 0.5, right? It's 10 below 200. So 10 divided by 20 is negative 0.5. So we're interested in this area in here. That's the probability that's the percentage of people in this population that have a cholesterol level between those two numbers. The only problem is our table will only tell us the area of this distribution from the point we tell it, like a Z-score of 0.5, all the way down to the bottom. In other words, this entire area in here, all the way down to the bottom. Okay, and if I do that again for 190, it will only tell me the area that's in here, right? So we need to know the area that's in between these two. Well, if I know what the area is here, so I'm going to make up a number. If I know that that's 60%, right? And I know it's more than 50% because it's to the right of the mean. It's more than half of the distribution. And I know this is less than half. And if I said below 190 is only 40%, well, if this 40% is part of that 60%. So if I subtract the 40% from the 60%, I'm left with 20%, which is the area that's left in between them, right? That's how I got that. Let's look at the real numbers. So first one thing I need is plus 0.5, which is plus 0.50 is 6915.6915. Okay, this is 0.6915, and this area for negative 0.5, oops, negative 0.50 is 3085, got 31%, 3085.3085. So if I subtract this from that, 0, 8, I use the old math, okay, 8, and moving, this is 3, right? So this area in here is 0.3830, or 38.3%. Right? So probability of selecting someone between those two numbers is 0.3830. Okay, so that's normal distribution. Now let's move on from normal distribution. Because unfortunately, a normal distribution for a population, let's say, we're never going to move on from the normal distribution. You might, in other courses, but not in this course. Okay, so let's move on from the normal distribution here. And let's take a look at applying the central limit theorem. Okay, which is what that idea of central limit theorem, that's the idea that we understand that there's a relationship between a sample, the size of the sample, and how that relates to the mean and the standard deviation of the population. Okay, so for starters, that's kind of what central limit theorem is. So let's say we take a sample of size 25. Before we took a sample of size 9. Let's say we take a sample of size 25 from this population that we were just working with. Right? Remember this population? Right? What was it again? The mean was 200. The standard deviation was 20. Let's drill again. $200 mu standard deviation is 20. Okay. Okay. Sample is okay. What's the probability that the mean sample, that the mean of that sample of size 25, what's the probability that the mean of that sample that I take is greater than 204 milligrams per 100 cc? It's greater than 204. Okay, well, I'm not really talking about the population anymore, am I? If I take a sample of 25 from this population, what's the probability that the mean of that sample of size 25, not one person randomly selected, but that sample, what's the probability that it will be greater than 204? Well, in order to understand that, in order to predict that, I have to understand, well, that's a sample of size 25. What if I took many, many, many samples of size 25? You would get, and then I made a new distribution out of those, new normal distribution out of those. Okay, and I'm going to draw it right here. Here it is. I'm drawing it a little bit skinnier, right? Not proportional. If I took thousands and thousands of samples of size 25, what would I expect the average value to be for the mean of those samples of size 25? We'd expect it to be the same as the population, 200, right? Because sometimes we'll, sample size 25, sometimes we get an average below, sometimes an average above, just like we did before when we did our little exercise there. Okay, now that's the mean of these samples. How about the standard deviation of these samples? Okay, would I expect the numbers, if I took 25 people and found the average and I put that into my spreadsheet, another 25 found the average, put it in my spreadsheet, would I expect them to be spread out as much as the population is? No, I would expect it to be a narrower distribution. You guys remember what that relationship was? The standard deviation is equal to the standard deviation of the population over, what was it again? The square root of what? The sample size, right? So what's our sample size here? 25. So the standard deviation of this distribution of samples, repeated samples, is equal to 20 divided by the square root of 25 is 5. So the standard deviation is going to be 4. So if I take a random sample of 25 people from this population, 68% of the time, I would expect the mean to be between what two values? One standard deviation below the mean and one standard deviation above the mean. But only thing is now this is a sample of size 25. So 68% of the time, one standard deviation below is 4 less than the mean, 196 to 204. Okay? That's the difference here, is that now our sample variability is compressed, right, because of the sample size. That's if it were size, that's if it were size, a sample size of 25, right? What if we're a sample size of 100? What's the standard deviation for these repeated samples? What would that be? Well, 20 divided by, well, square root of 100 is 10, 20 by, then it would only be 2. Standard deviation would only be 2. So these samples would be closer and closer together, the bigger that sample becomes. Okay, so what's the probability that if we took a sample, a single sample of 25 people from this population, that result of that sample would be, remember sample size 25, would be above, what was it again? 204. Okay, anybody want to tell me what the z-score is there for 204? 204 minus, what's the mean? 200 over the standard deviation for the sample distribution is what? 4. It's 4 over 4 is equal to 1. Right? So this is one standard deviation above the mean, right? Now if I go to my z-table, right? My z-table, well, first of all, the empirical rule is going to tell me this is 34%, and then this is 50%. So it's going to be around 84% or 0.84, right? Below 204, or 16% above. 16% of the time you get a mean for a sample size of 25, above 204. But I could go to my table and do it more precisely. Oh, it's asked for a sample size, the sample above 204. So we need to do this and subtract. So that would be a standard deviation of 1.0 is 0.8413 as we predicted. So below would be 0.8413, and above 204, probability of selecting of a sample mean being that high is going to be 0.8413 less subtracted from 1, which is going to be 0.1587. Okay, about 16%. Okay, so a little confusing, right? The important thing here is that you remember to distinguish between a population and a sample. So when we're examining a population, we're going to, and we know the mean and the standard deviation, we're going to use the z-table and the z-score. When we're working with a sample from a population, Well, those samples are going to be distributed in a manner that the mean is going to approximate, be very similar to the population mean, but the standard deviation is not going to be the same as sigma is. It's going to be sigma divided by the square root of the sample size. It's going to be a narrower distribution. Let me see if I got it. Let me see the next part of this problem. So if you're a little bit shaky on this, that's okay so far, because we're going to be playing around with this for quite a while. Okay, what's the probability that the mean of that sample is between 192 and 204? Okay, well, how about 192? How many standard deviations below 200 is 192? Right, 192 minus 200 over 4, right? That's going to be minus 8 over 4. So the z-score is -2. So that's 2 standard deviations below the mean. What area is left in here? 2 standard deviations below the mean is only 2.5%, right? 0.025. Right? Remember the empirical rule? 95% between 2 standard deviations below the mean, 2 standard deviations above the mean. So just save time not to go to the table. That's going to be 2.5%. Right? So if I want to know the area between these two, right? Well, that's going to be our area of 84% that we just found before, less 2.5%. It's going to be about 82%. In other words, we're playing around with these areas in the distribution, just like we did with the normal distribution. The big difference is that the standard deviation we're using is related to the sample size. Okay, so now let's wipe our minds clean of all that for a moment and see if we can come up with another example. I don't like that one. I got a better example here. Okay, oh, that's not going to work. There it is. I think I have another set of examples. No, I don't want to get into that. I didn't get that far. I'm going to make one up. I'll make one up. I think that's even better. I'll make one up that uses nice, easy numbers. Okay, I have a population. That population is normally distributed, and it has a mean of 100 and a standard deviation of 10. Okay. So I know that 95% of this population is between 80 and 120. Okay, I know that 2.5% of this population is below 80, and 2.5% of this population is above 120. I remember that from the empirical rule. Right? So let's say that I take a sample of size 25 from this population. Okay? Well, let me, instead of saying size 25, instead of saying a single sample, let's say I take many samples of size 25, and I draw a new distribution that uses the results of all of those means, right? Many, a million times. I do it a million times, right? So if I do it many times, I'm going to get a normal distribution, a better normal distribution. What is my mean going to be for all of those samples that I take? You guys think? Population means 100, right? What are my sample means going to be? They're going to be 100 also, right? So half the time I'll take 25 people, find the mean of those 25 people, and it's going to be below 100. Half the time it's going to be above 100, right? It's symmetrical, right? Okay, now what about the spread? The spread here, 95% of the population here was between 80 and 120, okay, because I have a standard deviation of 10. Okay, that's 95%. Okay, so now my sample means. What percentage of my sample means are going to represent the middle 95%? What range would 95% of my sample mean results would represent 95% of the sample means? Okay, well, how many standard deviations below the mean would that have to be? -2 standard deviations and +2 standard deviations, right? So what value would that be? The mean's 100, just like the population, but the spread, the standard deviation, is going to be what? It's going to be sigma over the square root of the sample size, which is going to be 10 divided by the square root of 25, which is 5, is going to be equal to 2. So what value, what mean, what two means represent, what range represents 95% of my results for the sample mean? Okay, what's going to be 2 standard deviations below the mean is going to be what? It's going to be 96, right? On here we shout the answers out here. What about 2 standard deviations above the mean? 104, right? 95, if I would take a sample of 25 people from this population, random sample of 25 people, 95% of the time, the mean that I got would be between, oops, went the wrong direction, but I guess. 95% of the time, the mean would be between 96 and 104. Would it always be between those two numbers? No, 2.5% of the time it's going to be lower, 2.5% of the time it's going to be higher. Right? How about between 3 standard deviations below and 3 standard deviations above? That's like 99.7, right? That's all, it's very small probability. Right? Well, what is 3 standard deviations below? That would be 94. And 3 standard deviation would be 106. So it would be very rare for us to take 25 people in this population and get a sample mean of anything less than 94 or bigger than 106. Very, very rare, right? Despite the fact there's a lot of people in this population that have a value under 96 or 94 or above 106, right? Because the sample distribution is compressed. So if I were to tell you that without knowing this, you don't know this at all, okay? If I were just, you don't know what the sample mean is. But I happened to tell you, somebody else did a study very similar to this for another population, for that population. Now we have a new population. The mean of this population is unknown. We don't know what the mean is of this population, right? Okay, so let's say that I were to say to you, the mean's not known, but from that other study, we know that the population standard deviation is equal to 10. I just happen to know it. And I'm going to say to myself, I don't know what the mean for this population is, but I have no reason to think the variability is different. So I don't know what the mean is, but I know the standard deviation of population B is equal to 10. If I were to tell you that we took a sample size of 100, right, and we found that X bar, our sample mean, I'm going to use X bar for my sample mean, okay, X bar came out to be 98, right? What's the standard deviation for repeated samples of size 100? Repeated samples of size 100 is going to be, let's see, it's going to be equal to sigma over the square root of the sample size. That's going to be equal to 10 over 10 is equal to 1, right? So 95% of the time, I would expect that my sample mean would be 2 below to 2 above the mean for the population, right? So if X bar came out to be 98, right? Well, gee, that would suggest that, that would suggest that maybe I can say to myself that I know something about the true population mean. I only took one sample, so I got 98. Do I know that that's the real mean? No, it's a sample. I mean, it could be wrong. It could be lower. It could be higher. I don't know which it could be, right? So do I know? I don't know that that's the real sample mean, but since I know the standard deviation of the population, I know how spread out the population is, and I know based on my sample size how spread out my sample means are going to be, I can say to myself, well, 2 standard deviations below this number and 2 standard deviations above this number. If I start out with saying that that's a guess for the sample mean, 95% of the 95% of the time, I might be able to say that my true population mean, my mean for my entire population, is between 96 2 standard deviations below that number and 100 2 standard deviations above that number. How did I justify saying that? I justified saying that by my understanding of the relationship between the standard deviation of the population and the standard deviation of my sample means based on the sample size. So I'm gonna do a new one. Take another one. Okay. So I'm going to ask you to give me the properties of the sample distribution. Here's my sample distribution next to our population distribution. Our population mean is 75. Our standard deviation is equal to 25. If I were to take repeated samples from this population of size 100, okay, what would I expect the mean of this, my sample distribution mean, and my sample distribution standard deviation to be? What do you think the sample mean is going to be? The mean for all of the repeated samples of size 100. What's the mean going to be? 75. It's going to be, no reason for it to be different, right? Because we're selecting 100 people at random from here. So we would expect it to average out to 75. Right? How about the standard deviation, the spread of all of my sample means that I took over and over and over again? 25 people got the mean. 25 people got a mean. Then made a new distribution out of that. Out of those means? What do you think the spread for all those values is going to be? Standard deviation is going to be equal to? Going to be what? Okay, let's see. It's going to be 25 over the square root of 10, which is 10, square root of 100, which is 10. That's going to be equal to 2.5. Great. 95%, if I take my sample means now, 95% of my sample means are going to be between what two values? Let's see, well, 2.5 is the standard deviation, so double that. 2 standard deviations below the mean is going to be 5, it's going to be 70. And 2 standard deviations above the mean is going to be 80. So 95% of my sample means are going to is going to be between 70 and 80. Yes. Because I'm using the empirical, remember the empirical rule where if we have a normal distribution, 95% of the population is between 2 standard deviations below the mean and 2 standard deviations above the mean. Why am I doing that? Because it's an easy number for me to remember. Yeah, I could have said, how about this? What percentage of the sample means, what percentage of them are between, say, if this is 75, what percentage of them are between 72.5 and 77.5, right? One of these is one standard deviation below, one of these is one standard deviation above. What percentage of the sample means are between those two? About 68%. I'm just picking it up. Yeah, I just chose that. Yeah, because I'm just describing how this works. In other words, I'm trying to help you relate to how the sample distribution relates to the population distribution, right? So in other words, going back to 95%, 95% of the people, remember standard deviation is 25, so 95% of the people are 50 less than that, or 25 to 50 more than that, which is 125. So that's the spread. 95% of the people are between 125 and 125, but 95% of my samples are between 70 and 80, right? See how they're compressed? So if you take a sample size 100, it really compresses the standard deviation for repeated samples. And again, the reason why we're interested in that is because let's say the sample size had only been 25 instead of 100, right? What would my standard deviation have been then? It would have been 25 over 10, or excuse me, it would have been 25 over 25, over the square root of 25, which is 5. It would have been equal to 5. This my standard deviation for my sample distribution. Since the sample size was smaller, my sample distribution is more spread out. So 95% of the sample means I would expect it to be 2 standard deviations below to 2 standard deviations above, which would be 65 to 85. So when that sample size got smaller, my sample distribution got wider. So I know less about where my population mean really is, right? My the location of my population mean now, how accurately, how reliably I know my population mean from taking a sample now got worse because it could be further away, for the same level of confidence. Okay? So that's what we're really after here. We want to use what we know about sample distributions to predict what the population mean is. Do we care what the sample mean is? Is it important to us what the sample mean is? We don't care what sample mean is. Sample mean is just a way for us to estimate the population mean. If I were to tell you, we just did a survey of all the nursing homes in New York City, and the average blood sugar level for elderly patients in these nursing homes is 117, right? For that for everybody, for all of them, 107. Well, you got the mean, but that's the average for the entire population. But now, if I told you that we took a random sample of 25 people in nursing homes in New York City, and the mean that I got was 112, right? The mean blood sugar level was 112. Well, that's interesting. Do I really care about those 25 people? I'm only using that as to guess at what the true population mean is. Why didn't I just measure everybody? Because I didn't have the resources to do it. You very rarely have the resources to measure everybody. So when you take a sample, you're not really after the sample mean. The sample mean is a means to an end, literally. I didn't mean to make a pun, but it's literally a means to an end. It's a way for you to understand or estimate what the population mean is. If I want to compare cholesterol levels for New Yorkers versus people living in San Francisco, right? I was just reading about all sorts of health food restaurants and food trends in San Francisco. And if I wanted to compare, maybe eat healthier than we do, whatever, I'm going to take a random sample of people in the same age range, your age range, for instance, right? I'm going to compare people in New York City to people in San Francisco. If I really wanted to know if there was a difference in the cholesterol level for people between 20 and 40 in New York versus people in 24 in San Francisco, the best way for me to do it, the most accurate way for me to do it, is to measure everybody in that age range in New York and get an average and compare it to the average of everybody in San Francisco. Is that practical to do? No. So how am I going to do it instead? I'm going to take a random sample of people in New York, compare it to a random sample of people in San Francisco. So now I say average cholesterol level in New York is in that age group is 150. Average cholesterol level in San Francisco is 130, right? Do I really know the population average for those two locations? No, I only know the means for the samples in those two locations. So is it possible that the cholesterol levels could really be the same? And just by bad luck, we chose people with lower levels in San Francisco and higher levels in New York when we took a random sample. That could happen, just by luck, right? So we need to understand how likely it is that we would get that big a difference between these two populations if we only have information from a sample of a certain size. That's what we're really after. How reliably can we predict what the real population mean is from a sample? So we kind of got an interesting idea here now. 2 standard deviations below, 2 standard deviations above, and this idea of 95%. Okay, let's take that a little further. Okay, so I'm going to go to this other document. Okay. So I'm going to take a sample of size 100, and this sample has a mean of 160. Now, I don't know anything about the population yet, right? I haven't said anything about the population. I took a sample of size 100, and the mean X bar of the sample is, what I said was 160, 160. And as it happens, I know that we took this from a population whose standard deviation is 30. Now, is that a stretch? Am I always going to know? Is it likely I'm going to know the standard deviation of a population? In other words, for everybody in that population, and not know the mean for that population? Not going to happen very often. But for now, to make the math simple, we're going to assume that we know what the population's standard deviation is. Unfortunately, later on, we're not going to know that. We're not going to know mu, and we're not going to know sigma. For the moment, we're going to say that we don't know mu, but we do know sigma. We're going to just make that assumption that we do know it, right? So if I know sigma, I can figure out what the standard deviation for my sample means are going to be. And it's going to be equal to 30 sigma over the square root of the sample size, which is 30 over 10, which is 3, right? So I can calculate what my distribution, what my spread is for my repeated samples of size 100 is for this population, samples from this population. So, okay, my standard deviation is equal to 3. I'm, for the moment, going to say to myself, 160 is my guess at what the population mean is based on this sample that I took, this one sample that I took, right? And I'm going to say to myself, well, I'm going to start from that 160, right? And I'm going to say to myself, if that were the real mean of this population, let's say for a moment that we really knew what the mean of this population was, and we took samples of size 100 from this population, well, I would expect 160, I would expect that 95% of the time, if I took that big a sample from this population, that my sample result, my mean from the sample that I took, would be between 3 standard deviations below the mean, which would be 2 times 3 would be 6, would be 154, to 2 standard deviations above the mean, which would be 166. So 95% of the time, I would expect to get a sample that's in that range. Well, I'm going to turn this around a little bit. And I'm going to say to myself, I don't really know what the mean is. I don't really know that it's really 160, right? I only have a sample mean that's 160. But let me turn this around and express this another way. If the true sample mean, if it had been actually, this is 160, 166, this would be. The true sample mean, it might be up here, it might be over here, it might actually be below 154. But 95% of the time, it's likely to be between these two numbers. Just like if I knew what the sample mean was, if I knew what the true population mean was, I would expect this sample that I just took that came up 160, I would expect 95% of the time it would be within that 95% for my sample distribution. So I'm going to turn it around and talk about the population mean being between these two numbers, 154 and 166. Okay, and I'm going to say to myself, okay, given that I know what sigma is, and I know that'll help me predict what my standard deviation should be, I expect that 95% of the time that I'm going to find that the true population mean, right? We don't know what it really is. The true population mean is going to be within 2 standard deviations of the mean that I got when I took my sample. And I'm going to call that, I'm going to give that a name. That range is going to be the range within which I'm 95% sure that the true population falls. So I may not know what mu is, but I'm 95% sure that it's between 154 and 166. And why am I sure about that? Because I understand how sample size impacts the variability of the samples that I'm taking, the results of the samples that I'm taking. Okay, and I'm going to call that, instead of calling it, instead of calling it something else, I'm going to call it a level of confidence. I'm 95% confident that the true population mean falls between these two numbers. And we call that the 95% confidence interval. Okay, so now let's say I take another sample from another population. Okay, and this, let's see, there's some population. I know the standard deviation is equal to 10. Whoops, 10. My sample, I take a sample, size 25. My mean, X bar, comes out to be 55. And my standard deviation for repeated samples of size 25 from this population, which has a mean that's completely unknown, right? My standard deviation for this population is going to standard deviation of repeated samples is going to be the standard deviation of the population, sigma, over the square root of the sample size, square root of 25, is going to be equal to 10 over 5, is going to be equal to 2, right? So now I'm going to take my mean, check out for my sample, and I'm going to add and subtract 2 standard deviations from that. Okay, so my mean is 55. I'm going to add and subtract 2 standard deviations. Standard deviation is 2. That's 2 times 2 is 4. So I'm going to say that I'm 95% sure that the true mean, that mu, is between 51 and 59. Okay, and I picked those 2 numbers. Why did I pick 2 again? Somebody brought that up before, pointed out I used 2. Because it's the 95%, because it'll capture 95% of the possible samples I would get from that, from repeated samples of that size, right? What if I had picked, instead, I had picked, let's say I had picked 3 standard deviations instead. What would 3 standard deviations be? It'd be 2 times 3 is 6, right? What was it, 49 to 61, right? One. Well, hang on a second. That's 3 standard deviations, right? So 3 standard deviations. What percentage of the population is within 3 standard deviations? Or what percentage of normal distribution is within 99.7, right? So what level of confidence do we have that we have the mean is between those 2 levels, right? Well, there's only a tiny bit, that 0.3%, that is the probability that we would miss capturing the mean between those 2 levels, okay? Because we're willing to go further out. Okay, so I'm going to ask you a quick question here about this idea of confidence intervals. Okay, 90. I'm going to say 95% confidence interval, and I'm going to say 90% confidence interval, and I'm going to say 99% confidence interval. Which one of these confidence intervals is the widest? Do you think? Is 99% the widest, or is 90% confidence the widest? 99? Who says 99? I see a couple of hands. Who says 90? I see one hand for 90. 90% is the widest. Why is 90% the widest? I'm sorry, excuse me. 99% is the widest, right? Why is 99% the widest? Why is 99? Because we want a high level of confidence that we've actually captured the mean. So we want it to be as wide as possible. 90% confidence, we're willing to be less certain that we capture the mean. So that means we can make the range smaller, right? So 90% confidence interval is smaller than a 99% confidence interval. 95% confidence interval is in between them. Yes? No, hang on a second. 3 standard deviations would be 99.7. Okay, now I'm really going to make things complicated. Okay, they're not really complicated. I'm going to make them more accurate. Sometimes that's more complicated. In this case, it's not really more complicated. I'm going to write a formula down here, okay, which we're going to live with for the rest of the semester. X bar plus or minus, okay, I'm going to put Z in here. Z times the standard deviation, right? In other words, Z is the Z-scores. So in other words, if I want a 95% confidence interval, what would Z be? Be 2. 2 times the standard deviation for the sample distribution, right? If I want, oops, wrong direction. Okay, so for 95%, what would I use for Z? X bar, I'm going to make up numbers. I'm going to say X bar is equal to 100, sigma is equal to 20, and sample size is equal to 25. So standard deviation is equal to 20 over the square root of 25, which is 4, right? So X bar would be 100. That's my sample mean, plus or minus the number of standard deviations, which if I want 95% confidence, I want it to be wide enough that 95% of the time I'll capture the population mean, right? I would use a 2 in there, except there's a slight problem here. Remember, the empirical rule is only an estimate, right? What really represents, when I talk about the 2 standard deviation, 95%, and 2 standard deviations below and 2 standard deviations above, I'm talking about this being 95%. And since the normal distribution is symmetrical, this bottom part should represent 2.5%, 0.025, and the top tail should represent 0.025, right? Because that's how much you miss on both ends with 95% in the middle. So let's go to our Z-table. And let's look up what the number of Z-scores really is for an area of 2.5%. In other words, I'm going to go to this table. What Z-score would I need for this tail to represent 2.5%? So I'm going to go dig into these areas. There was a problem similar to this on the exam, right? Where you had to look up an area in here. There might have been, I don't remember. Okay, so let's look up 2.5% here. So 2.5%, the area 2.5%, here it is right here, 2.025. That is represented by a Z-score of, it's not 2. 2.0 is over here. 2.0 is 0.0228. In other words, 2.28%. But 0.025 is really 0.196. So the Z-score that represents 95% or 2.5% on either side is really 1.96. The empirical is just an estimate. I put it, and we use the 2, right? Close enough for government work, right? In the beginning, but now we want to be more accurate. Times 2, instead of 2, 1.96 standard deviations. What was the standard deviation for our sample based on a sample size of 25? It's 4. So our 95% confidence interval is going to be 100 plus or minus 1.96. Oh, I see where, I'm not going to figure it out. I'm just gonna say that it's gonna be 1.96. 2 times that is about 8. It's approximately 92 to add, uh, add 8 to that add 8 to that is 108, right? Okay, now what about my 99% confidence interval? What would I use there? 90% confidence interval. The only thing that would change there is the z-score that represents 99% and the z-score that represents 90%. That z-score for 99% is going to be 2.58, and the z-score for 90% is going to be 1.64. 2.58 is going to give you a bigger number you're going to subtract and add to 100. You're multiplying by a bigger number, so it's going to be a wider interval. 99% confidence is going to be wider interval. If you're willing to accept more chance of error, 90% is only going to be 1.64 instead of 1.96 times 4. It's going to be a narrower interval. So 90% narrower interval, 99% wider interval, 95 in between. We're a bit ahead of the lecture here because the lecture is really going to cover confidence interval next week. But the real key here is that the understanding that we tried to get about how sample distributions work is what's going to help us understand how well a sample, how reliable a sample is in giving us what a population mean is. Because that's really what's important to us. We'll never know when we take a sample, we'll never know how close we are to the true population mean. But we can at least know that within this range, we would, at this level of confidence, we would expect that the true population mean lies.